Now talk about Coulomb's law in the second part of the electrostatics. By the end of this section, you'll be able to state Coulomb's law in terms of how the electrostatic force changes with the distance between the objects. You'll be able to calculate the electrostatic force between two charged point forces, such as electrons or protons. You'll be able to compare the electrostatic force to the gravitational force for a proton and electron, and so on and so forth. So this section is dedicated to completely understanding Coulomb's law. So we basically want to understand how Coulomb's law came into practice. Experiments show that the electric force between two charges is proportional to the product of the charges and inversely proportional to the distance of separation between them. So through the work of scientists in late 18th century, the main features of the electrostatic force, that's the existence of two types of charges, the observation that like charges repel, unlike charges attract, and the decrease of force with distance, were eventually refined and expressed as a mathematical formula, which Coulomb derived or gave us the mathematical formula for the electrostatic force of repulsion or attraction. He was a French physicist and was named as Charles Coulomb, and he between the years 1736 to 1806, and his contribution in the field of electrostatics and electricity is huge. He performed experiments and first proposed a formula to calculate the forces between charges. Based on his experiment, he gave us the following formula, where it says the electrostatic force. This is the electrostatic force. He defined that the electrostatic force is actually proportional to the product of the magnitude of the two charges. If there are two charges, for example 1 and 2, then he also proposed that the forces decrease as the distance of separation between the charges increases. So there is an inverse square law between the distance and the charges. So we have seen a similar effect in the gravitational force as well. If the two objects move farther and farther away, the gravitational force decreases. In the same way, the electrostatic force between the two charges decreases with distance. So we call those as inverse square rule. That means as the distance drops, the force reduces by 1 by r square. So he combined these two, just like in the gravitational force. He combined the two together to give us a combined formula where we said magnitude of Q1, magnitude of Q2, and over r square. So in order to remove this proportionality sign, he needed to replace the proportionality sign with a certain constant. And he worked on it and experimentally found that the number came out to be a certain number that we'll soon define. But then he inserted that constant with the symbol K, which was Q1 over Q2 over r square. So the full formula is given as K times Q1, Q2, although I would like to put a magnitude in front of it because it's the magnitude of the force. So given by this number. So what is the value of K? He experimentally found that the value of K is actually 8.99 cross 10 to the power of 9 Newton meter square over Coulomb square. So it's based on the units of force, which gives us the Newton in the unit, and meter square is the unit of distance that we have over here, and the unit of charge is Coulomb, so Coulomb square. In the same way, we have gravitational force Fg. It's very similar to that, which is where instead of the charges, we have masses m1, m2, over r square, where g is gravitational constant. Here we have k, which is electrostatic constant and has a certain value. In short, we also sometimes write it as 9.0 cross 10 to the power, in some 10 to the power of 9 Newton meter square over Coulomb square. In some books they use 9.0, in some books they use 8.99. And the gravitational constant here is 6.67 cross 10 to the power of minus 11 Newton meter square over kg square. So that's the difference between the G and the K. We use Coulomb square instead of kg square. So both are very, very similar rules. But gravitational force is much weaker than the electrostatic force, because the electrostatic force is exerted at the atomic level, and hence they are far more stronger than the gravitational forces. So in order to understand the electrostatic forces, let's understand this diagram. What does this mean? If we have two charges, say Q1 and Q2, they are like charges, so the force between them will be repulsive as assumed. Then how do you read F21 and F12? So F21 is the force exerted by 2 on 1. So there's a force between the two. The 2 exerts a force on 1, and the direction is in this way because it's repulsive. And the force exerted by, if you see, if you look at that, the Newton's third law applies here, and we say the Newton's third law, that every force creates an equal and opposite force. The Newton's third law applies here as well. The force on Q1 is equal in magnitude and opposite in direction to the force it exerts on Q2, because they are like charges. And as in part B, we have unlike charges, hence the forces are attractive. They tend to point towards each other. So this is a repulsive force, and this is the attractive force because of the nature of charge. While as in gravitational force, it's always attractive, so that's a difference. So yeah, in order to understand these diagrams, you should know the terminology. When we write F12, it is the force on 1 due to 2. Force exerted by 1 on 2. And F21 is read as force on 2 due to 1. So we have also done this kind of thing in, if you remember, forces chapter in physics 151, where we were also talking about force exerted by one object on the other, while as the second object also exerts the same force on the first one due to Newton's third law. So if there are two like charges, the force exerted on one by 2 will point this way, and the force exerted by 2 on 1 will be this way. So force exerted on 1 is pointing this way, and the force exerted by 2 on 1 is this way, because they are repulsive. So in the same way, if we have two negative charges, the directions will be opposite. F12 and F21 will be in the opposite direction. But if we have unlike charges, force exerted by 1 on 2 will point towards 2, and the force exerted on 2 by 1 will point towards 1. So that's because of the attractive and repulsive nature of the two charges. It's how they are aligned. So the unit of charge you all know is Coulomb, and the proportionality constant is actually, so that's Newton meter square. Let me rewrite this. This is K is equivalent to 8.99 cross 10 to the power of 9 Newton meter square or Coulomb square. It's also acceptable to write 9.0 cross 10 raised per 9 Newton meter square over Coulomb square. So charges produced by rubbing are typically around a microcoulomb, because 1 coulomb charge is huge, and we don't usually write 1 coulomb when the two charges that are interacting will be usually of millicoulombs or microcoulombs or nanocoulombs, as I talked about in part 1. So charge on a single electron or a proton is same. The magnitude of the charges are same, although for electrons we use a minus sign, and for charge on a proton will be plus 1.6 cross 10 to the power of minus 19 coulombs. So electric charge is quantized, as we said. Q is equivalent to plus minus Ne. We even looked at it in the part 1. So please remember that Q is the total charge on an object. It can have millions of electrons or millions and billions of protons and positively charged particles. It can have, this E is the charge of an electron or a proton. That's why we put plus minus sign in here. So we have already discussed this in part 1. You must be wondering what this K is equivalent to. It was found mathematically actually equivalent to 1 over 4 pi epsilon naught, where epsilon naught is called the permittivity, electrostatic permittivity of free space. So you don't have to worry about this. We'll normally be using K, and if at all we are using epsilon naught, at that time, that's when we will talk about electric fields and all, we will need epsilon naught at that time. But for your Coulomb's law problems, you will probably not be using epsilon naught. So we will hold on to this value until then. Epsilon naught is the absolute free permittivity of free space, and the value is 8.85 cross 10 to the power of minus 12 Coulomb square Newton meter square. So when we come to the electric field part, we will use this again. But for the Coulomb's law, you should definitely use K value, magnitude of charge 1, magnitude of charge 2 divided by r square, the distance of separation between them, where K is either 8.99 cross 10 to the power of 9 Newton meter square over Coulomb square, or you can also use it as 9.0 cross 10 to the power of 9 Newton meter square over Coulomb square. So either one of them will be fine for calculations. So let's get started with our very first problem from the textbook, which is what is the magnitude of electric force of attraction between an iron nucleus, which has the iron nucleus has 26 plus 26 protons, and its innermost electron, if the distance between them is 1.5 cross 10 to the power of minus 12 meters. So we are using, these are all based on Coulomb's law. So, and we will use the formula F electrostatic force is equivalent to K times magnitude of charge Q1, magnitude of charge Q2 divided by R square, which is the distance of separation between the two charges. So go ahead and pause the video and try working on this yourself and see what you are going to plug in. So electron, there is one electron in the innermost shell, and the nucleus, you are actually talking about nucleus where there are neutrons and protons, but neutron is chargeless quantity, so these are the charges due to the proton. So if you want to find out what is Q1, it is plus 26 times the charge of the protons, which is same as 1.6 cross 10 raised by minus 19 coulombs. And Q2 is the electron, that's the charge of the electron, okay, single electron which is revolving around the nucleus. That's what it is saying. So we know our Q1 and we know the charge on the electron, so we can go ahead and plug in the values. Before making sure that you're plugging in the right numbers, make sure the units are in SI system, no conversion is needed. So we go ahead and substitute. These will require a lot of attention because these are bigger numbers or smaller numbers, and you should be putting your calculator in proper settings. Fe is 9.0 cross 10 to the power of 9 because the value of K, which is a constant, is 9 cross 10 to the power of, I would use 2 sig figs, or you could also use 8.99. So 8.99 cross 10 to the power of 9. I'm skipping the units here. They are all in SI units. So the end result for the force should be in newtons, although the unit of K is Newton meter square over Coulomb square. So Q1 is 26 times the charge on a proton, which is same as electron. Cross the magnitude of the charge will stay same. And the other one is the charge on electron, 1.6 cross 10 raised by minus 19. So be very, very careful about calculating and putting these numbers in the calculator. You may want to try this a couple of times. And R square is the distance of separation, 1.5 cross 10 raised by minus 12 meters whole square. So start plugging in the values and make sure your final answer Fe should be in 2 sig figs, and you should be able to solve this correctly if you put all the units properly and you should be getting 2.7 cross 10 to the power of minus 3 newtons. So the electrostatic force between the 26 protons and 1 electron in the iron atom is of this order. So next problem, we will work on the repulsive force between two protons, which is which is at a distance of 4 points. This is, I think, number 4. What is the repulsive electrostatic force between two protons, which if you want to calculate that at a distance of 4.0 cross 10 to the power of minus 15 meters apart, that's the R value for you. And so we again go ahead and use the formula F is equivalent to K times magnitude of Q1 magnitude of Q2 over R square. In this case, the Q1 is equal to Q2 is are the protons, is the charge on proton, and which is 1.6 cross 10 to the power of minus 19 coulombs. So we can simply write 8.99 cross 10 to the power of 9 Newton meter square over Coulomb square, and your charge 1.6 cross 10 raised power minus 19 coulombs, and we have 1.6 cross 10 to the power of minus 19 coulombs. Dividing that throughout, make sure your PEMDAS is in the correct order here. R is 4.0 cross 10 to the power of minus 15 meters whole square. These are how you solve the Coulomb's law of forces. I like to write Fe for this to give you an idea that this is an electrostatic force. So please pause the video and punch in the numbers in your calculator properly and go ahead and get the value. So this is actually a huge attractive, this is a huge force, not attractive. These are two protons, so they will be repulsive force, and it's of the order of 14.42 newtons. So this is what your calculator might show, and then you round it to the 2 sig figs that are given in the problem. The final answer you display is 14 newtons, which is a 2 sig fig. So now we work on number 7 problem from your textbook, which says that there are 2 small charged spheres. So if we have 2 small charged spheres of, they are, let's name this as Q1 and let's name this as Q2, separated by a distance of R, which is 6.52 centimeters. Immediately you should convert this into meters, which is 10 raised per minus 2 meters, or you can divide it by 100, so it will be 0.0652 meters. So for me, this is the quickest to write it as 10 to the power of minus 2 meters. They are moved, and the force each exerts on other is found to have tripled. So if we move it a certain distance that the force that the other exerts on it has tripled, how far apart are they now? So basically you have to find new R. So if I call this as R1, your job is to find out the new R2 when they are moved a little bit and are adjusted. So since the magnitude of the force is inversely proportional to the square of distance, so if the force is tripled, then the distance has to reduce by a factor of 3. So if you write down F1 is equivalent to K times Q1 Q2 whole divided by R1 square, and the new force F2 should also be K times Q1 Q2, but it says they are moved, we can put this as R2 square for now, and if they are moved and the force each exerts on the other is found to have tripled, so how far apart are they now? So if you find the ratio of the two, and if we say that the force has tripled, so we can say that the force If the force is tripled, then the distance must have been reduced by a factor of √3. Does that make sense? Because if the force tripled, so what will happen to the distance? You can actually calculate this by putting them, by taking the ratio of this. So if F1 over F2 is equivalent to 3, if the ratio, it can be 3 times F2, we take the ratio. So you can just find this out. So F1 will be K times Q1 over Q2 over R1 square. Or you can also say 3 times F2. So instead of putting 3 times F2, you can say, we can also write this as F1 is equivalent to 3 times F2. K times Q1, Q2 over R2 square. Your job is to find this new R2. If you see this whole thing goes away. And we therefore have the same, let's rewrite this whole thing. 1 over R1 square is equivalent to 3. If you go back, it's 3 over R2 square. So basically your R2 square will be equivalent to 3 over 3 times R1 square. So if the force is tripled, the distance R1, the R should be, or maybe we are doing the other way around. So let's take a look at it. It should be F2 is equivalent to 3 times F1, not F2 is equivalent to, the force is tripled because of the new force is 3 times F1. So that's the equation that you use for this one. Sorry about that, but now we can take a look at it. And then F2 is K times Q1. Let's redo this on the backside and rearrange the equations. So the force is tripled. That means the new force F2 must be 3 times the force F1. And if you like K times Q1 over Q2 over R2 square must be equivalent to 3 times K times Q1 Q2 over R1 square. All we know is R1. The answer is in terms of R1 and R2. So you need to find R1, R2, R1 is already known to us. So go ahead and plug in the numbers. Okay, so by rearranging the terms and to get R2, so R1 square over 3 is equivalent to R2 square. If you rearrange the terms, this is what you'll get. So therefore, the force, if the force is triple, the distance must be reduced. The new distance must be reduced. Force will only triple if the two charges are of unlike charge. So the forces will increase. It must be attractive force. And so you go ahead and take the square root of all of this. It will be R1 square over 3. That is R2. The new R2 will be like this. So that will be R1 square over √3 is R2. Sorry, R1 over square root 3. Go ahead and plug in the values and we can find out either in centimeters or in meters. So if you put 6.52 centimeters, you can use either centimeter or meter in this case, because we are just finding the distance in centimeters and no other conversion is needed. So the distance has dropped to 3.76 centimeters. So that's how you will approach these types of problems, and be careful of reading the problem carefully, like mistakes can happen. So F2 should be 3 times F1. The new force is tripled. So if you make an error, just like you must have seen how the error can creep in, make sure that you're reading the problem carefully. The last one in the Coulomb series that we'll work on is comparing the electrostatic force with the gravitational force, and it's a very interesting problem. between the two charges. So if the electrostatic force holding the electron in orbit is which is at a distance of 0.53 cos 10 raised per minus 10 meters around the proton nucleus. So proton nucleus of hydrogen atom has one proton and one electron. So we know that we can compare the two. We know the mass of the electron and the proton. So let's see what all is given to us. So if we have a proton here in the nucleus and we have a electron in the external shell, one electron and one proton here, and the distance of separation between the two is r is equal to 0.53 cross 10 to the power of minus 10 meters. So mass of the electron is 9.11 cross 10 to the power of minus 31 kgs. Please use references for masses and all in your textbook. And mass of the proton is 1.67 cross 10 to the power of minus 27 kgs. The r, which is the distance of separation, is 0.53 cross 10 raised per minus 10 meters. And the charge on a proton, that is Q of E and P, is plus 1.6 cross 10 to the power of minus 19 coulombs. Charge on electron minus 1.6 cross 10 to the power of minus 19 coulombs. So we have all the information to calculate the gravitational as well as the electrostatic forces. Also one more thing, K is 8.99 cross 10 to the power of 9 Newton meter square over Coulomb square, which is the proportionality constant for electrostatic force. And the gravitational constant, which is the universal gravitational constant, is G is equal to 6.67 cross 10 to the power of minus 11 Newton meter square over Coulomb square. So we have all the information now to apply the two formulae. So we go ahead with and first finding the electrostatic force. So we'll find the electrostatic force between the two electron and a proton and hydrogen atom using the formula K times Q1 QP Q2, which is, I'm taking the magnitude of the charges, so the negative sign will not matter, divided by the distance of separation. So go ahead and substitute the values and pause your video here and do the entire math and come back and check your solution. So I'm sure that you are solving this while I'm doing it as well, and it's always better to do the math work yourselves. So punch in the numbers correctly and you should at the end get the electrostatic force between the two charges in hydrogen atom as 8.19 cross 10 to the power of minus 8 meters. Your job is to find out first the gravitational force and the electrostatic force, and then find the ratio of the two forces and find out which one is greatest. So that's why it's an interesting problem. So now we go ahead and solve the gravitational part of the electron and proton. What is the gravitational pull between the electron and proton will be given by G times mass of the proton and mass of the electron divided by the distance of separation, which is same as electrostatic force. So I gave you the values in the previous slide, so go ahead and solve for this one as well. So if you're coming back after punching in and calculating the values, you can check the math here. 6.67 cross 10 to the power of minus 11 Newton meter square over kg square, and mass of the proton 1.67 cross 10 to the power of minus 27 kgs, and mass of the electron 9.11 cross 10 to the power of minus 31 kgs, which is lighter, divided by the distance of separation, which is 0.530 cross 10 to the power of minus 10 meters whole square. Again, I'm hoping that you are punching in the numbers correctly by keeping the PEMDAS order in mind, and go ahead and get the value. So your answer for this should come out to be as 3.61 cross 10 to the power of minus 47 newtons. The gravitational force between the electron and proton is way less than the electrostatic force, which was 8.19 cross 10 to the power of -8 newtons. So you can compare and see how strong the electrostatic forces are. So then in the next step, you go ahead and find out the ratio of Fe over Fg, which comes out to be equivalent to 2.27 cross 10 to the power of 39. What it means is electrostatic force is 2.27 cross 10 raised power 39 times that of gravitational force. That's what it means. So it's 10 raised power 39 times stronger than the gravitational force. In the next part, we will talk about electric fields.